Hello. We're going to start this movie with proof of the MMC concept. This is objective number 4. Um, so the whole point here is what the validity is of using the bonus tolerance in an MMC modifier. When you're using an MMC modifier, you're allowing the hole position to add tolerance as the manufactured hole size increases. So the feature size affects the allowable position tolerance. So MMC allows greater freedom in part production, and working near the MMC limits, might make it easier if you have to rework the part later. I mean, so let's say you're working at your MMC, and you make a hole towards the MMC size and you find out your positional tolerance isn't in. And then you come back later and say, well, I can rework that hole by opening it up to a greater size to buy me some more positional tolerance. And that's perfectly valid when you're using the MMC. And the whole idea with using MMC is that you want your parts to fit without any interference issues. If there's a pin sticking over your part and then you have to put another part over top of that pin, you want to make sure that your positional tolerances are tight enough such that your holes are going to line up and they're always going to fit. So that's what the MMC modifier is for. So let's take a peek at this next slide and see if I can do this justice. Okay, so here's the proof of the MMC concept. So you got this plate here. It's made with pins in it. These pins are of the perfect size and position. Okay, so then you got another plate that fits over top of it. Okay, and this other plate that fits over top of it has one large hole that's off true position and it's loose fit on the pin. And then you got this other one, this smaller hole. It's like right on position and it's a snug fit on the pin. So when we look at the small hole, here's what we got. Okay, so we have our available tolerance zone here. Okay, and if we shove the top piece, the plate with the clearance holes, all the way to one side such that it contacts here, we've got this much clearance. Okay, and then that's the center of the pin and the true position, and here's the center of the hole. Now if we look at the large hole, it has a bigger hole on it, therefore it has a greater clearance. So if we shoved it all the way off to one side, that bigger hole is going to have more clearance. Okay, and really, how much more clearance is it going to have than the smaller hole? It's going to have extra clearance based on the size. So for every thousandth that this larger hole is bigger than the smaller hole, it's going to have a thousandth more clearance. And so that's really what we're saying. And that's really how bonus tolerance works, is as I make this hole bigger, as this hole deviates from MMC, I can allow additional tolerance and my parts will still fit. Okay, that essentially is the proof of the MMC concept, and that for every thousandths I open up my tolerance of the for every thousandths I open up the size of this hole, this produced hole, for every thousandths I open that up, I pick up another thousandths positional tolerance. So that's why we're saying that hey, if we're in a manufacturing environment and we're working towards the MMC and we screw up like on a position or something like that, well, you can go back and rework that hole to buy yourself more tolerance. And that's really how it works. As that hole gets bigger, you're afforded more clearance, and as you're afforded more clearance, you can use that extra clearance in terms of allowable positional tolerance. Okay, so that's the proof of the MMC concept. It really is for clearance of holes and how to assemble your parts. So that's why we use MMC. Okay, let's talk about fixed versus floating fastener conditions. There's some tables and there's some formulas and stuff in your textbook, but I've made this Objective 5, differentiate between the fixed fastener versus the floating fastener conditions. So we're really not going to do any calculations on this, but this is what this means. In a excuse me, in a fixed fastener condition, you have two pieces that are bolted together, but the one of the pieces, in this case, this threaded hole here, fixes the location of the screw. Okay. In this case, with the floating fastener, we have two through holes. The bolt goes clear through both pieces, and a nut is put on the end. So that is a floating fastener condition. And you can really have more positional tolerances allowable with this condition. Once you start fixing a hole, you got a little bit different conditions. So let's talk about the floating fastener conditions. The fastener passes through multiple clearance holes. A nut holds the assembly together. It's common to use the same size clearance hole for all parts, but it's generally not required. And again, when we talked about the proof of MMC concept, as long as our parts are going to fit, we can give it extra tolerance to assure that it's going to fit. So that's the floating fastener condition. Now the fixed fastener condition exists when the fastener passes through multiple holes and one hole fixes the fastener location. Now this could be fixed by threads, or it could be a press fit, or it could be a taper, or it could be any other feature that prevents fastener movement. And essentially what the fixed fastener does, it fixes the location of that one fastener. So only one part fixes the locations. Therefore, we need to make sure that we have enough clearance on the other holes to handle the tolerance. Okay, so here's your fixed fastener condition. The fastener passes through multiple holes. One fixes the location via threads, press fit, or taper. So that's what that looks like. Let's talk about additional tolerances or bonus tolerances. The tolerance value in the feature control frame applies when controlled feature is produced at the MMC size when MMC modifier is shown. So if you use the MMC modifier on the tolerance in your feature control frame, the MMC condition applies. It's allowed when feature sizes depart from MMC, and really additional position tolerance is allowed within the virtual condition as manufactured hole size departs from MMC. Let's take a look at an example at that. Okay, here's the allowable tolerance, hole position tolerances at MMC. This is an example for a hole. Okay, so here we have an allowable position tolerance, either sum of specified tolerances and additional tolerances, or difference between the produced hole. Okay, so what we have here is we have a 1/2 inch hole plus 6 minus nothing with a 35 thousandths MMC tolerance. Okay. Here in this table right here, we're showing what our positional tolerance is going to be versus what our produced hole size is. Okay, so at the MMC hole size of a 1/2 inch, we get a positional tolerance of 35 thousandths. But just like the proof of concept here, for every 1/1000th we increase our hole size, we gain an extra thousandth in allowable positional tolerance. Okay, so what we have here is that at the absolute least material condition of 506, that's the biggest hole, effectively we have 41 thousandths of positional tolerance, which is 35 thousandths plus 6 thousandths. Okay, so in this example right here where they're highlighting this box right here, okay, they're saying, well, if we produce the hole at 503 thousandths, and the MMC size is a 1/2 inch, then our additional tolerance is going to be 3 thousandths. Okay, and then at that condition, our specified tolerance is 35 thousandths from our feature control frame. Our additional tolerance, or bonus tolerance, is 3 thousandths. Okay, that's based on where we produce this hole, and then that equals our allowable tolerance. Okay, which is 38 thousandths. Now the other way to look at this is that if you took our produced size and you subtracted from it the virtual condition, you get an allowable tolerance of 38 thousandths, which is just what we're showing here. And this slide just goes over it a little bit bigger, but that's really what it is. And then what we're going to do is we're going to start with the same example, except applying it to the pin in the next movie. Thank you.